Alright, we are back and we are going to finish up our discussion of nomenclature here. I'm going to go over just a few examples of these just to make sure you sort of got the process down. Alright, let's see. Let's try this one. Okay, let's say we had that and then that. Okay. Alright, so in this case, I think should be pretty apparent that your longest continuous carbon chain is going to be 8, right? So that's going to be our parent. So we're going to be working with octane here. Alright, we have two substituents. We have an ethyl group and we have a methyl group. Alright, now we got to number it. This is going to be one of those cases where you're going to have a tie, right? If we go left to right, we have substituents at 4 and 5. If we go right to left, we also have substituents at 4 and 5. So what do you use? You use the alphabet. E for ethyl comes before M for methyl, so it's going to win. So that means we're going to number it from left to right. Okay? All right, so again, we put our names, our substituent names down alphabetically. So we're going to have a 4-ethyl group. And then we also have a methyl group at number 5. Ooh, did I leave enough room? I did. Woohoo. So yeah, this one would be called 4-ethyl 5-methyl octane. Okay? Alright. Let's try this one. Okay. Alright, the longest continuous chain in this one is going to be 5. It's going to go that way. Alright. That's going to correspond to pentane. Alright. And if you look at this, I think you can see that numbering it from right to left is going to be the way to go here, because that gives you your first substituent at 2 instead of 3. Alright, so you have 2 methyl groups, right? So that's going to be dimethyl, and they appear at carbons 2 and 3. So that is going to be 2, 3. Dimethyl pentane. Easy peasy. Not too bad, right? Alright, let's try a couple more. Alright, let's do work with a bigger structure. Ooh, okay. Now we got to do a little bit of thinking here, because it's not quite as obvious where the longest carbon chain is. So let's see. If we just did straight left to right with that middle chain, it'd be 1, 2, 3, 4, 5, 6, 7. Let's see, if we started up on the top carbon, we could go 1, 2, 3, 4, 5, 6, 7. Hey, guess what? We have a tie for the parent chain. All right, we could go like this, or we could go like this. Okay, either way, we have a longest continuous carbon chain of 7. Alright, so what was our rule? Well, our rule is we use the one that gives us more branch points, more substituents. If you follow the dotted, the parent chain in a dotted line, that would only give us 3 substituents, but if we did it in the one with a solid line around it, that would actually give us 4 substituents. So the one in the solid circle is going to be our parent. All right, and that is 7 carbons, so that's going to be heptane. So we got that. All right, so let's number it. Do we want to number it left or right? Well, in this case, it's pretty easy to see. I think if we start numbering from the right carbon, then it's going to give us a lower number. So we're going to have 1, 2, 3, 4, 5, 6, 7. All right, and if you look here, 3 of these groups at 2, 3, and 5 are going to be methyls. So we're going to have a trimethyl. I'm going to just write that up there, sort of out of the way. And then the other group on carbon number 4 is going to be a propyl. Okay, so which one do we write first? Well, again, remember we write these in alphabetical order, and we have the weird quirk. We don't count the T for tri, we count the M for methyl, P for propyl. So propyl is actually written last. So I can just go ahead and write that down right in front of the parent. Propyl heptane, and the propyl group's on number 4. All right, and then we have trimethyl, and that is going to be at carbons 2, 3, and 5. So we put those all in a series, 2, 3, 5. So 2, 3, 5, trimethyl, 4, propyl heptane. Rolls right off the tongue. All right. Hopefully you're starting to see now, some of these sort of intimidating sounding, names. Once you sort of get used to the process and following the rules, it's really not that hard to do it. It just sort of sounds like a lot, before you've really, gotten the hang of it. Once you get the hang of it, it's nothing. All right, let's try this one. Ooh, this is a beastly looking one here. Let's see. What? It didn't draw it? Dang it. Okay, let's see. Holy crap! This one looks kind of miserable, right? Not too bad though. All right. Again, follow it systematically. Find the longest continuous carbon chain. All right. I'm going to do that in my head for a second, so bear with me. All right. If you look through carefully, I think you'll find that this is going to be your longest continuous carbon chain, which is 10 carbons long. That is going to be decane. All right. And we have 4 different substituents. Okay. Hopefully you should be able to recognize that you want to start numbering left to right, because numbering it left to right gives you your first substituent at a lower number. So we got 1 at 2. We got 1 at 3. We have another group at 5, and a group at 6. All right, so let's see. I'm going to just sort of write these off to the side so I can keep up with them. We have a methyl group at carbon number 2. We have an ethyl group on number 3. On number 5, we have a, what is that? That is a sec-butyl group. And at number 6, we have methyl. So we can just basically sort of combine the 2 methyl groups at 6 into a dimethyl group. All right. So let's looking at these. So we have E for ethyl, B for sec-butyl, and M for dimethyl. All right, so dimethyl is going to be last, so I'm just going to go ahead and write it down here. Dimethyl at 2 and 6. All right, then we have E for ethyl and B for sec-butyl, so ethyl is going to be here. And we would write sec-butyl first. So, that's a mouthful. 5 sec-butyl, 3 ethyl, 2 6-dimethyl decane. This is something that you can impress your friends with, but yet learn pretty easily. So, hey, you want a party trick, a really sad one that probably nobody will like, There you go. All right. At this point, I'll be usually asking for questions. This is a really good start to naming acyclic alkanes. So there's, again, lots more practice problems, so be sure to be working on those and let me know if you have any questions. All right, one thing we haven't talked about yet is how to name cyclic alkanes. Those are very similar, just a little bit different. Okay? All right, so you remember how in the table of alkanes we had, methane, propane, butane, hexane, all these things. All right, these corresponded to parent chains. You're going to start off the same way with cyclic alkanes. You want to find your parent, right? But in this case, it's not. We don't call it a parent alkane. We call it a parent cycloalkane. And we actually use this group, cyclo, as a prefix. To name your parent here, what you do is you add the prefix cyclo plus the name of the alkane. It looks ugly. I want to erase it. There you go. The name of the alkane that corresponds to the number of carbons involved, right? So if you have something like this, right? There's 3 carbons in this ring. It's cyclic, so this would be cyclopropane. Right? This one has 5 carbons in a ring. Cyclopentane. 6 carbons in a ring. Cyclohexane. You get the idea that these look like just a bunch of polygons, and that's basically what it is. But it does correspond to the number of carbons within the ring. You just name the alkane according to the number of carbons and add the term cyclo, the prefix cyclo to it. That's all you do. Okay? So identification of the parent ring is usually pretty easy with this. All right? Once you find the parent ring, you got to number the carbons in the ring. Okay? And really, for doing this, it's essentially the same rules. You're going to try to number it to try to give carbons with substituents the lowest possible number. You'll have ties. If you have ties, you follow the same guidelines that you did before. You don't necessarily go clockwise or counterclockwise. Sometimes you'll go clockwise, sometimes you'll go counter whenever you're doing this. Right? It just depends. Okay? For example, if you had something like this. Let's just say you had a cyclohexane and then had a methyl group on it, right? By definition, we want the first carbon to be the one the closest to a substituent, right? Well, in this case, with a cyclic alkane, if we just have one substituent, this carbon that has the substituent will be carbon number 1. That makes it very, very easy. Okay? In fact, in something like this, because it's understood to be at carbon number 1, you don't even have to write 1-methyl cyclohexane. Although if you did, I wouldn't mind, and I wouldn't count out for it, but since it's understood, you can just write it as methyl cyclohexane. No matter where you put the methyl group, that methyl group is going to be on carbon number 1. Okay? It gets a little bit more thought-provoking whenever you have more than one substituent. All right? Let's say you had something like this. And actually, what I'm going to do is I'm going to work with this one. All right. Let's say, actually, I am going to adjust it a little bit. Let's say we had this. Okay, we have 3 methyl groups. All right, we're trying to figure out which one's going to be carbon number 1, which way we're going to go. All right, again, what we want to do is we want to give as many substituents as possible the lowest possible numbers. If you started over here and made this one number 1, then if you went clockwise, the best you could do would be to have this one be 3 and this one be 4. So that would be one possibility. However, what if we made one of these number 1? Let's say we made this one number 1. Okay? If we made that one number 1 and we counted counterclockwise, we could have 2 and 4. So in this case, we actually have 1, 2 instead of 1, 3. And as we learned from the previous rules, 1, 2 is better. Right? So when you're trying to number these carbons here, keep that in mind. Try to give the substituents the lowest possible number in order of appearance. Okay? If you had one like this, all right? Now this one's interesting because either way, you could. There's a couple of different ways you could have 1, 3. You could have this one be number 1 and go clockwise 1, 2, 3, or you could start at this one, go counterclockwise, and go 1, 2, 3. So that seems to be a tie, right? Well, what did you do before when there was a tie in this regard? You're exactly right. I'm assuming that you got it right. If not, just play along. We are going to use the alphabet. All right. So since we have a tie for positional tie each way, since E becomes before methyl, this guy gets. Whoops! I had my eraser on. Dag nabbit. Well, you guys get the idea. The ethyl group, the carbon with the ethyl group was number 1. Okay. And then the third part and the fourth parts are basically the same as we saw before. Name your substituents and identify where they are. And then put everything together. All right, so again, I'll do a few examples for you. Say we have this, right? Okay, so your parent ring here is going to be cyclohexane. So we can go ahead and write that down. All right, we have 2 methyl groups. All right, so we're going to have a dimethyl. Now, if it was just one methyl group, you could just have it understood that it would be at the number 1 position, then you could just say methyl cyclohexane. However, with dimethyl, there's multiple possibilities. If they're on the same carbon, that means they're both on number 1. But however, they could be on different carbons, right? So in this case, you do need to specify that it is 1, 1 dimethyl cyclohexane. Okay? Let's try another one. Let's try this one. All right. Okay, in this case, this is going to be another one of those ties where you could go one way and have substituents at 1 and 3, or go the other way and have the same thing. So it would be good to go ahead and name these 2 substituents to see what they are. All right. This is going to be an isopropyl, and this one's going to be a tert butyl. Okay. So if you remember our alphabet conventions, we go I for iso, B for butyl, so the tert butyl group's going to win. It's going to be at carbon number 1. Okay? All right, so we're also going to put these in order alphabetically. So that's 1 tert-butyl. Three, isopropyl, cyclopentane. All right. 1 tert-butyl, 3 isopropyl cyclopentane. Okay, let's try this one. All right. So, in this one, we have a cyclohexane. We have 3 substituents. All right. It should be fairly obvious that in this case you want to make this guy carbon number 1, because if you made that one number 1, you have 2 substituents of number 1 instead of just 1. It doesn't really matter whether we go clockwise or counterclockwise. Either way, this guy ends up being number 4. All right. This is a butyl. This is diethyl. E for ethyl, B for butyl. So this is going to be 4-butyl. 1, 1 diethyl cyclohexane. All right. Okay. Hopefully those have helped you sort of at least get at the initial swing for doing this. Keep doing some practice on those. And let me know if you have any questions. There's one more situation I want to show you really quickly. There are going to be certain cases where you might have a situation like this. Let's say we had this with a 5-carbon chain on it. Okay. This case is a little bit different because, all the examples of cyclic compounds we've seen so far have had have had the rings being the parents. However, you will run into some cases where you have a ring with an acyclic carbon chain on it, and the acyclic chain is larger than the ring. In those cases, the larger part is the parent. So in this case, the straight chain part would be the parent, and this guy would be the substituent. Okay? So your parent chain is 5 carbons. It's going to be pentane. How do we name cycloalkanes as substituents? Well, you basically follow the same rules that we did with others, right? You could take cyclopropane. What you do is you erase the A and E and you add YL. So to name a cyclic alkane as a substituent, you do the same thing as you would if it was acyclic. So this becomes a cyclopropyl group. And it's on carbon number 1 of this chain, so it is 1 cyclopropyl pentane. Okay? Probably more often than not when you encounter rings, they usually tend to be parent chains, but not always, certainly. And so being able to recognize that will be important. Okay. That ends the discussion of nomenclature for now. This is basically, the entire version of alkane nomenclature. Not gonna lie, this is probably my least favorite part of OChem to teach is nomenclature because, honestly, it's a little bit dry. But hopefully, you guys will, get the hang of it. Usually, the students love nomenclature because they regard it as being the easiest part. So we'll see what you think of it. If you have any questions at any point, though, please let me know. I'll be happy to help. Until next time, I will talk to you later.